In this video we're going to learn more about row-reduced echelon form. If you can't remember the definition, now will be a good time to go and look it up. Here are two facts about row-reduced echelon form. First of all, given any matrix A, I can do a sequence of row operations to reach a row-reduced echelon form matrix. That's fairly easy to convince yourself of if you just practice doing row operations to a given matrix. If you'd like a proof, you can find one in the online notes. It's not too difficult to do. The second fact is much more difficult and is not at all obvious to me. What it says is that if you've got a matrix A and you can do row operations to A to reach a row-reduced echelon form matrix B, and if you can also do some row operations to A and reach another row-reduced echelon form matrix C, then actually B is equal to C. So there is one and only one row-reduced echelon form matrix which can be reached by doing row operations to your matrix A. You can find a proof of this in the online notes. I don't intend to do it here because we don't actually need it. But it does explain something about the way people talk about row-reduced echelon form. You will often hear people say the row-reduced echelon form of a matrix A. And what they mean is the unique matrix in row-reduced echelon form which can be reached by doing row operations to A. Fact 1 here means that at least one such row-reduced echelon form matrix exists, and fact 2 means that there really is only one row-reduced echelon form matrix which you can get to by doing row operations to your matrix A. So let's look at an example of doing row operations to a given matrix in order to reach a matrix in row-reduced echelon form. We'll start with our matrix up here in the top left. So the 3 by 3 matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. And we're going to do some row operations to this in order to reach a matrix in row-reduced echelon form. So a sensible start would be to eliminate the entries in the first column. You'll remember that part of the definition of row-reduced echelon form is firstly that every leading entry must be equal to 1. Well, we can see the leading entry in row 1 is 1 already. And also, every entry in the column of a leading entry must be 0. So we should eliminate the 4 and the 7 in column 1. We can do that by subtracting 4 times row 1 from row 2. And that's the first row operation there. It takes you to this second matrix here. And then we can eliminate the 7 from row 3, column 1, by subtracting 7 times row 1 from row 3. That's the row operation notated here. And what it leads you to is this matrix right here. Now if you look at this matrix, row 2 has a leading entry -3 in position 2, 2. But in a row-reduced echelon form matrix, all leading entries have to be equal to 1. In order to make that happen, let's multiply row 2 by -1/3. That's the row operation notated here, and the result is this matrix here. You can see that rows 1 and 3 haven't changed, but row 2 now has leading entry 1. Again, all of the entries in the same column as a leading entry must be 0. So we need to eliminate the non-zero entries in column 2, row 1, and column 2, row 3. We'll eliminate the 2 in position 1, 2 of this matrix by subtracting 2 times row 2 from row 1. When you do that, this is the matrix you end up with. Now we need to eliminate the other non-zero entry in the same column as our leading entry in position 2, 2, which we can do by adding 6 times row 2 to row 3. That's the row operation I've written here, and the result is this matrix here. We've now reached a row-reduced echelon form matrix. The only row of zeros is at the bottom, so that's fine. The only leading entries are this one, and they're both equal to 1. The only entries in the same column as the leading entry are 0. And finally, the leading entry in row 2 is to the right of the leading entry on row 1. This matrix satisfies all 4 conditions for being in row-reduced echelon form. Now let's look at an example of solving a linear system whose augmented matrix is in row-reduced echelon form. Here's the augmented matrix. You can check that that really is in row-reduced echelon form. Let's look at the equations it corresponds to. So we'll give some names to the variables in this linear system. Let's say x, y, z, and w, and then the last column corresponds to the constants on the right-hand sides of our equations. As I've said before, some people put dots or a dotted line in their augmented matrix like this. I won't do so, but if you want to, that's fine with me. So what are these equations then? The equations are, first, x plus 2z is equal to 0. Second equation is y plus 4z is equal to 0. The third equation says w is equal to 0. And the last equation says 0 is equal to 1. This is impossible. There are no solutions to this linear system because one of the equations is impossible to satisfy. On the other hand, consider this different row-reduced echelon form matrix. Again, let's give names to the variables in the system which this augmented matrix corresponds to. We'll call them x, y, and z, and w. The equations this time are from the first row I get x plus 2z is equal to 2. From the second row I get y plus 4z is equal to 3. From the third row I get w is equal to 4. And the fourth row, well, the fourth row says 0 equals 0, so the fourth row doesn't tell us anything at all. We might as well actually miss this off. In any event, you can now read off the solution straight away. You can choose a value for z freely, and then all the other variables are determined uniquely once you've done that. If you choose your value for z, then x is equal to 2 plus 2z, y is equal to 3 minus 4z, and w is equal to 4. So there's one variable, z, which can be chosen freely, and then every other variable is determined uniquely once you've made that choice. In this situation, we call z a free parameter. Here's the general method for reading off the set of solutions to a linear system whose augmented matrix is in row-reduced echelon form. There are 3 steps. First of all, if the last column of the augmented matrix has a leading entry, there are no solutions. That's because when the last column has a leading entry, it means you've got an equation of the form 0 equals 1, and there are no solutions to an equation 0 equals 1. If not, then there are solutions. At step 2, we observe that variables corresponding to a column with no leading entry, like z in the example we've just done, can be chosen completely freely. Those things are called free parameters. Every other variable is then uniquely determined in terms of these free parameters. We now have a complete method for solving any system of linear equations. First of all, you write down the augmented matrix associated to that system. Next, you do row operations to the augmented matrix until you reach a matrix in row-reduced echelon form. You know from our theorem earlier that when you do this, you don't change the system of linear equations. So the system of linear equations in row-reduced echelon form has precisely the same solutions as your original system. Finally, you can read off the solutions to the row-reduced echelon form system using this final slide, and you know that those are the same as the solutions of the system of linear equations that you started off with.